We're Group 7 presenting our research for EAA Semester 2 2020. I'm Akila and this is my group.
I'm Athena.
I'm Nishtha.
I'm Elsa.
I'm Xin. Our team has explored on how enterprise architecture frameworks can facilitate the effective use of big data in smart cities.
In this presentation, we will sequentially explore relevant background, research question, methods, and outcomes of our research. Globally, 55% of the world's population lives in cities or urban centers. In Australia alone, 70% of the population live in capital cities. This disproportionate distribution of population density, along with population growth, presents challenges in quality service provision within these urban centers. In response to these urbanization challenges, smart cities leverage the use of information technology to promote sustainable development and deployment of services to its citizens. This infrastructure is largely made up of Internet of Things sensors transmitting data over the network and other means of capturing voluminous data. This data captured, analyzed, and managed assists government, enterprises, and citizens in making informed choices to improve the quality of life. The volume and type of data generated in smart city initiatives have led to the adoption of data lakes. Data lakes are large repositories that cater to the collection, storage, and analysis of mostly unstructured data, therefore making it a better choice than structured relational databases. However, data lakes pose complexity in governance and design, and in ensuring that the data delivers the benefits that align with the smart city vision. We know that the enterprise architecture frameworks provide the guidelines and principles that aid in the strategic alignment of ICT initiatives with the goals of the enterprise. The most common ones are Zachman Framework, TOGAF, and FEAF. The Australian Government Architecture, AGA, is a derivative of the FEAF and used in the Australian context. Given the challenges of big data repositories and background of enterprise architecture frameworks, we wanted to explore our research question. How can enterprise architecture frameworks facilitate the effective use of big data in smart cities?
To explore our research question, we firstly conduct a literature review to understand the current research direction. We then analyze this review and identify the gaps in the research. Based on the identified gaps, our research methods was adopted to begin addressing these gaps. By reviewing the current literature related to the smart city, big data, and enterprise architecture, we identify three gaps. Firstly, there is a lack of holistic view in discussing EAF application in smart cities. Current research only focuses on deploying EAF to particular areas, such as the smart transportation or smart tourism. Secondly, challenges outlined are limited to the 6V or 4V characteristics of big data, from a technical perspective with limited social-technical considerations. Thirdly, there is a limited justification of a particular EAF, such as TOGAF and Zachman, and lacked a justification on why those attributes of the selected EAF are the best in addressing these challenges.
To begin addressing these gaps, we broadly explored four potential challenges that hinder the effective use of big data in smart cities: visibility, reliability, imagined behavior, and reusability. These challenges are beyond the current limitations in research that present the 6V or 4V characteristics of big data as challenges. We then adopted examples from the Smart Darwin strategic plan to clarify the potential appearance of such challenges in real-world initiatives. The Smart Darwin plan aims to use big data in multiple applications. Therefore, drawing examples from this plan addresses gaps in research that only focus on a particular application area, such as tourism or transport. Lastly, we mapped each challenge to attributes that underlie popular EAF frameworks to demonstrate how such an approach can identify and provide justification on why or what EAF is best to account for these challenges.
Big data presents a visibility challenge. As the number and type of smart city data resources vary, it decreases the visibility of the type, method, and purpose of data collected. 4 EAF attributes are selected to address this challenge. Taxonomy completeness helps categorize data from multiple sources to enable transparency of the process. Petitioning guidance enables autonomous petitioning of the enterprise to manage the complexity of data usage in the system environments. Business focus ensures the data collected and processed are to drive business value. Reference model guides help to build a set of interrelated models that will increase the transparency of data flow. Together, these attributes help to address the visibility challenge. The second challenge is reliability. The various data resources and the heavy investment on different types of data capturing infrastructures have led to several data reliability issues, which may potentially affect the quality of service provided. We selected 4 attributes to address this challenge. Governance Guide provides a reliable governance model to increase the adaptability to changes. Practice Guidance helps to educate and guide people through the changes. Vendor neutrality reduces the dependency on specific vendors for expertise regarding the EA framework. Information availability ensures accessibility of information resources regarding the framework. All these 4 attributes will help to increase the reliability of big data in smart cities. Emergent behavior is a third challenge. Things can get really dynamic around big data in smart cities. For example, data points can add up during processing. It can be combined or divided for different purposes, and the socio-technical and legal landscape can be changed. EA framework will help to reduce the complexity and react quickly to those emerging behaviors. Taxonomy completeness enables more efficient access to data when necessary through a clear categorization of data. Governance guidance provides a comprehensive and reliable guidance on how to process data for different purposes and ensures the legal compliance is met. Process completeness provides a complete and clear process to map out how new data activities or changes within the enterprise architecture. Reference model guidance provides a solid foundation through the use of reference models that support variations such as emergent behavior. Petitioning guide enhances objects of data usage for or reusability by dividing and combining data for different parts of the enterprise. Business focus aligns information technology to smart city objectives, such as increasing the quality of service to citizens and cost reduction. The fourth challenge is reusability. The problem of data integrations manifests in smart cities as they seek to grow their efficiency in the use of big data, along with the growth in data collection opportunities. 5 attributes are selected to address this challenge. Time to value increases the likelihood of reuse if data structures and frameworks exist before using it to deliver higher business value. Maturity model measures and evaluates the effectiveness of EA in each department. Based on the evaluation results, we can determine whether it can be reused in the future. Prescriptive catalog guides the setup of a catalog of architectural assets that can be reused in the future activities. Reference model guide fosters reusability through standardization it provides. Taxonomy completeness categorizes data artifacts to enable reusability. And a specific and complete process can encourage reusability. Together, these attributes will help to increase the reusability of big data in smart cities.
Upon mapping the 4 challenges to the attributes of EA frameworks, we applied the scoring technique devised by Sessions and colleagues to compare Zachman, TOGAF, and the FEA model. As we explore challenges in the context of an Australian government-based smart city plan, we have swapped in AGA as it is the Australian counterpart of FEA. The aim of this scoring was to understand which of the 3 popular EAF frameworks best support the attributes needed to address the challenges. The results varied for each challenge. TOGAF and AGA both have equal strengths in addressing visibility, whereas TOGAF is suitable for addressing imagined behavior and reliability, and AGA is more suitable for reusability. Overall, TOGAF scored slightly above AGA and significantly better than Zhang in its potential to address the sum of all challenges.
In this paper, we focused on addressing the gaps found out in the literature review and hence tried to justify the use of one framework over the other. The paper uses scoring approach to analyze each framework based on some attributes. However, the paper does not apply the selected framework to the smart city plan. Also, in the EAF scoring table, which we saw in the last slide, it can be seen that the difference between the scores achieved by TOGAF and AGA is not that significant. And this paper does not explore the implication of choosing TOGAF over AGA. However, the paper takes a deeper look into how the attributes of different EA frameworks addresses each challenge individually. Additionally, there are only 4 challenges identified for the smart city plan, but there can be many other challenges that can be explored and scored. It can be seen that TOGAF has lower ranking in some of the attributes when compared to other frameworks. For example, in case of taxonomy completeness, Zachman has a higher ranking because it provides a comprehensive framework for organizing artifacts from various perspectives. In case of maturity model, AGA stands on a higher ranking. This is because of its performance reference model, which helps in identifying the effective data that can be reused in other applications. In case of perspective models, again, AGA has a higher ranking because of the specification of standards for data within the data reference model, which enables further ease of reusability and interoperability between various agencies within Smart City Initiative. In case of reference model guide, AGA again has a higher score because of its performance reference model, which can help in rating the different reference model to determine the most effective one. It can be concluded that with the growth of population in different cities of Australia, it is now very important to use the data collected effectively to build up a smart city, which fulfills every citizen's need. Enterprise architecture can play a very crucial role in aligning the data with the smart city objectives. Although many research papers have utilized EA frameworks to address the big data issues in smart city projects, but a few of them have laid the base for by defining the method to select EA framework. Hence, in this paper, we used EA framework attributes scoring matrix to evaluate and compare Zachman, AGA, and TOGAF frameworks. This would enable enterprises to select the most suitable framework for their identified challenges. By analyzing Darwin's smart city plan, we identified 4 challenges, that is visibility, emergent behavior, reliability, and reusability. Further researchers can work on a larger set of challenges to evaluate the EAA frameworks and identify the one which is suitable for their enterprise. This was all from our side. Thank you.